Welcome back, my steel design friends. Up to this point, we've spent a lot of time talking about the design of tension members with regards to strength and doing calculations like gross yielding and net fracture. But in a practical sense, that's not all there is to it. You also have to consider something known as serviceability, and in this video, I'm going to show you how to do that. So without further ado, let's get started. Whenever we get into structural design of members, whether they're tension members or compression members or beams or whatnot, there are always two criteria that we look at that are deemed the structural adequacy criterion, okay? The first one is strength, and this is the one that we've looked at up to this point. This includes things like gross yielding and net fracture, and in the case of tension members, there will be several others that we'll look at later on in this series, things like block shear or bolt strength or tear out failures and several others that we'll take a look at. But there's a second one in there that is not strength related, okay, and that is what is known as serviceability. Okay, and serviceability affects things like deflections or vibrations or usability of a structure. Things that are a little bit harder to quantify but do have an impact on how a structure is used or its perception of quality. Okay, and in particular with tension members, vibrations can be especially damaging because they can also cause fatigue in a connection. If you think about a member that's in a building, if it's subjected to a vibration, it's moving back and forth and wiggling continuously. So, if you've ever taken, an item like a paper clip or something in your hands and you've, unfolded it and then bent this thing back and forth without going very far, but eventually over time it gets harder and harder and then eventually it will break. That's a fatigue type failure. That's what we're worried about not having happen in our structures when we're designing with steel, because the same thing can happen. Now you may not break the member, but you might break a weld on a connecting plate, or you might prematurely fail a bolt or something, or an area in the net fracture area around a bolt may be weakened as a result of that. So we want to be careful that we're taking this into account for serviceability. Now, AISC section D1 shows us that the requirement for serviceability, and it's a very simple requirement. If I flip back to here and I go, it's basically table D3.1, one page before. This gray box right here is the slenderness limitation. Okay, and you can see that what it says is that for members designed on the basis of tension, the slenderness ratio L over R preferably should not exceed 300. Okay, now it doesn't apply to rods or hangers in tension, but other members like angles or W sections or whatever, this is the criteria that we're going to use and we're going to try to stick to. Now, the idea of this, L is the length of the member, and R is going to be the least radius of gyration. All right, so let's talk a little bit about those section properties, because this is really one of the first times in this series that we've dealt with the radius of gyration. Okay, and so I have a kind of a sheet here that will kind of go through some things and some factors that we want to keep our mind aware of as we're working through this. Okay, so the radius of gyration, let's start with what we call a doubly symmetric member, such as an I-beam. Okay, it has two axes of symmetry. It has a horizontal axis X and a vertical axis Y. Okay, we can compute the principal axis or the principal radius of gyration as being Rx being the square root of Ix over Ag, or Ry being the square root of Iy over Ag as we look at this. Now, one thing special that that you cover in advanced mechanics classes is that we know that these members when they're symmetric, we knew that back in mechanics materials, symmetric bending was stress is equal to MC over I or My over I, depending on the form that you saw in your textbook. But what we didn't often clearly state when we were studying our analysis of this is that the product moment of inertia for a doubly symmetric shape is 0. Okay, it's because of the symmetry. Now, what really happens in this, and I'm going to use kind of a Moore's circle analogy to this, is that if I plot, we know that this member here has an Ix and an Iy associated with its, what we call its principal axes, okay? And it turns out that this Ix is, for an I-beam, is typically the largest, and Iy is usually the smallest. Okay, and so what happens is if I plot this kind of like a Moore's circle kind of thing, on there where I put the moment of inertia that I'm looking at on the horizontal axis. This is your IX or IY, and your and then the product moment of inertia on this vertical axis. Now I'm not too worried about the sign on this. We can put positive IXY up. We don't do any of the more circle manipulations we did with stresses and strains. Okay, but we get an arrangement that looks like this, and the points that this IX and IY, this principal axes, would plot here for IX, because it's the larger of the two, that's your principal 1, and here for your IY, that's your principal 2. Okay, and so you can see that there is no larger possible I value than IX, and there's no possible smaller value for IY. Okay, that's what doubly symmetric looks like. Now consider a shape that isn't that way, say maybe an angle or some sort of unsymmetric shape. Now potentially there's an axis of symmetry that acts along here. If I look at IX and IY, now IXY is not equal to 0 for this particular shape. And if we go and plot this, now we end up with, instead of plotting down here on the principal point like we did when it was doubly symmetric, now I'm plotting here. Okay, and so this would be IX comma IXY, and then on the opposite end would be my IY, and I plot a negative IXY on this one. Okay, and what you notice is that the largest value on this circle is no longer IX. It's actually over here, and it's a function of this angle and how far up this whole diameter has rotated on our Morse circle, if you will, for moments of inertia. Okay, now, and likewise, the minimum is no longer IY. There's actually a smaller value in this guy. I mean, this guy is coming up, and this is the one that's going to control the direction of the deflection. Right? So what happens is that this angle corresponds to an alignment of an axis. It's kind of like those rotated elements, that if this is X and Y and this is my centroid, there's a Z axis that lives in here that is inclined at some principal angle from that. Okay, and so it's this guy, the major axis is relative to Z, or the minimum is relative to Z, but the major is relative to this guy that's happening along here. So it's this RZ value that is our minimum radius of gyration. It's not Rx and it's not Ry anymore. It's this RZ value. And you can see that in our tables for angles. If I go pull one of these up for us real quick. That when we look at, say, and I'm just grabbing one at random, even these guys are pretty big, and I know I'm zoomed way in here, but if I look at like an L12 by 12, here's my Rx over here, 3.64. Here's my Ry, also 3.64. This is because it's a square, equal legs on this. But take a look at your RZ value. They actually reported it's 2.3. It's almost 30% less. Okay, and this is the guy that will control. And in the case of using a single angle as a member in tension, I can get penalized pretty severely by this number being so drastically different than the Rx and Ry, all because of this concept of unsymmetrical bending and the Rx-Ry relationship. Right, so that's kind of what we're looking at on that. So like I say, there's a whole big side discussion that we could go into for how do you calculate stresses under tension, how do you calculate stresses under bending. Just kind of make you aware of there is a difference between these. This is what you saw back in mechanics materials, but this is what's going to happen in practice a lot of times when we try to do a single angle and make it work for us. Okay, but this will also be the key to a trick that we can do in our framing to kind of help us out, and we'll talk about that next. All right, so here we go. All right, so if we go back to our basic criteria, I've got an example here that I kind of want to look at for say a frame that is 30 foot on center, and that's reasonably typical normal spacing for column lines and bays, and then a floor height of 15 feet. And I'm just going to put a brace along here, and we'll say that maybe this is subjected to some sort of lateral load, either from wind or seismic or something that's happening on this. Let's play the L over R game for this guy. Okay, so if I'm 30 feet this way and I'm 15 feet this way, then the diagonal will be somewhere around 33.5 feet. Again, approximate. We're just kind of playing an approximate game here. If I am bound by L over R less than 300, the R minimum of this guy is a 1.34 inches. Doesn't seem like a real big number, okay? But the problem is that our selection, if this is a single angle, is going to be based on the smallest of Rx, Ry, or Rz, okay? And if we go back and we pull up our pull up our manual again and go looking for an RZ value that is greater than that value of 1.34 inches, okay, you can see that now I'm looking, 8x6s don't work, 8x8s, we're looking at these values, those guys will work. We're up to an angle that is 8x8, at a minimum. So let's just say we take the lightest one, which is a half, and use that as our first guess. Okay, we can do some calculations. Now, you could use 10s and 12s, those all work, but anything less doesn't because of the L/R criteria. Okay, so if we do that and we look at it, we can record that the gross area is 7.84 square inches. The weight of this guy is actually 26.4, and we'll make note of that and kind of show you kind of our comparison. If I calculate just the gross yielding, because this is kind of the theoretical maximum load this member can take without worrying about connection details. Okay, so if I do this, it's, VPN is 0.9 AGFY, and if I plug in all my numbers, again, we're assuming A992 just for the sake of argument on this. Okay, 0.9, 7.84, 50 KSI. This guy can hold 353 kips. Okay, and that's a pretty massive tension load in a building, especially for, a diagonal brace that's subjected to wind. In fact, kind of as a typical load for wind on a relatively short structure that is, 3 or 4 stories tall, this guy might get to 20 or 25 kips. So we've over-designed this thing by a factor of almost 10 times. Okay, probably more than that, more like 12 or 13 on this for relatively short buildings. For larger buildings, you've got to do something a little different because you do get some big forces. But for relatively short structures, 4 or 5 stories tall, this is significantly overkilled, over-designed. Okay, now let's just, for the sake of argument, go in and calculate what's the weight of this member. 26.4 pounds per foot at 33.5 foot for this member. This thing weighs 890 pounds. Okay, you cannot move this with 2 people. You will need a crane, a man lift, multiple people to move this thing just to get it into place. It is a very big member. Okay, so that's kind of a problem just from a construction standpoint. How do you deal with that? Okay, all right, so let's go through and let's take a look at what can we do or how can we fix this problem. Okay, and the first one, so our 2 options are, since we're playing with L/R, our 2 options are we must change either the length or get rid of that RMin that's hurting us, particularly for single angles, doing away with RZ. Okay, basically eliminating this and finding some way to use a symmetric section on this. Okay, so the first one we'll look at is just changing the length. Okay, one of the ways that we can accomplish that is by, instead of doing, a diagonal where we have this, and often what happens is, these come in pairs. And so maybe I have another one this way, and then maybe there's another one here. This is what we call as an X brace. Now, I don't have to do it, but often they come in that pattern. And if you look at a steel building that's being framed under construction, often you'll see X's running around. That's what they're doing, that's the lateral bracing. Okay, so my options is that I can do something instead by changing the length and do what we call a K or a V brace pattern. And so what happens, instead of connecting it to the corners, I now connect it to a plate that's connected in the middle of the beam. All right, and so then this end is still down here and this end is still over here, but instead of going all the way to this diagonal, I'm now only going to here. I've cut this length in half to 15 feet. So 15 feet up, 15 feet over. If we look at it, my L is now 21.2 feet. Okay, which is, a length savings of about 50%. Okay, so if I do the same gain that we just did, L/R less than 300, my R minimum, if I do my calculation, ends up being 0.852 inches. Okay, and if I look at my manual for this, you'll find that there are several sizes that start to work. Okay, and we will go into here. Okay, and so if I come and I look, we're looking at things like, I'm on the next page over, playing with the single angles over here. 5x5s look like they'll work. Okay, even the 6x4s will start to work. So again, we'll take the lightest one, 6x4 by 5/16, and 5x5 by 5/16, all as a comparison. It turns out those 2 guys basically have the same area. Okay, and thus the same weight. Okay, so if we look at the weight, that's our selection criteria. The lightest one is generally the lowest cost. Okay, so 10.3 pounds per foot for both of those guys. The gross area is somewhere around 3.07. I think the 6x4 is 3.03 and the 5x5 is 3.07. They're basically the same. Okay, so we'll play with those. And let's run the calculations out again. My gross yielding on this guy, doing the same calculation, 0.9 AGFY tells me it's 138 kips in tension. Okay, now again, 20 to 30 kips is what I need. I've got 138. Well, we're still over-designed by a factor of about 6x. Okay, but take a look at what happened to the weight by doing this pattern. Now I take 21.2 feet times 10.3 pounds per foot times 2, because now there are 2 of them, okay, and my total weight is 437 pounds. This is about half the weight of what that first requirement was. Okay, still pretty heavy and still needs some special considerations, but definitely a lot better for working with than that big old monster 8x8 that we're looking there. Okay, so we've improved. Okay, but we can do better. Okay, because the problem that we had in both the first 2 cases was that we were being controlled by an RZ, as our R min value. I was forced into that RZ column. But what we can do instead is, if instead of doing RZ, I decide to go and do something known as a double angle arrangement, would be something like this. Whether it's long leg back-to-back or short leg back-to-back, doesn't matter. They're 2 angles that work together, have some sort of gap. Usually there's a plate or something in there, and then these guys are connected to the plate, and it basically ties these 2 as a unit to each other. Okay. Now, if you look at my shape, this guy is now singly symmetric. Okay, and what that means is it means that our IXY for this guy is again 0. Okay, which is good, because when IXY is 0, RZ is no longer present. Okay, I only have an RX and an RY through a centroid. Here's my X, here's my Y. RZ doesn't exist, because if you think about it, RZ on this guy is that direction, but RZ on the other one is the other, and they're kind of fighting each other. They cancel each other out. Okay, and so that's good news for us. Okay, so now we have lots of options on what we can choose for sizes, but let's just kind of take a look. L is still the same, 21.2 feet. Our minimum is 0.852 inches. Okay, and so what happens is that now we're just going to, just for the sake of argument, just choose something that has equal leg angles, which is actually a decent idea in fabrication, because if you have an angle that is unequal, 6x4 or 5x3.5, you got to be very careful that the fabricator that's putting holes into these members puts the holes in the right leg. Okay, unless you're putting holes in both legs. Okay, whereas if it's equal legs, it's harder for them to mess that up. Okay, but let's just say, the first one that we find out of the table, and I won't show it in the manual, you can look this up, is that the L 3x3, actually a 2L 3x3 by 3/16. In fact, I will show it to you. Okay, just to kind of see what happens on this. If we go to this page right here, we're now looking at up here in the 2L 3x3 family. Okay, and so we have our values are kind of up in this range, and in order to get above our 0.854, you look, the RY for long leg back-to-back, or even the short leg back-to-back, okay, starts to happen on this, is that all of the RY directions now are stronger than the RX. So the RX direction, which is that horizontal axis, if you look down here, this horizontal axis is the one that's controlling on our vibration. All of these work, whether I do short leg back-to-back, well, these are equal legs, so they're going to be the same value. But if you look, all of those work. So let's just take then and say we'll take the lightest one. So this is going to be 2 angles 3x3 by 3/16 down here. Okay, and so that will be our shape. Okay, and that's where it's coming from. Okay, our RX now controls. We have an RX of 0.933. That's greater than what we required for 0.852. Okay, the gross area of a single one of these 3x3s is 1.09 inches squared and has a weight of 3.71. Wow, the units are way off, pounds per foot on that. Okay, do gross yielding calculations. Now I have, phi AGFY, so 0.9 times 2, because again, there are 2 of them, okay, that are experiencing the load. 1.09 square inches is the area, and 50 KSI. We're now at 98 kips. Now we're only at a 3x factor. We're still over designed, but not nearly as bad. But here's the kicker on this. My weight on this is going to be 2, because there's 2 of them here. Okay, and then there's 2 for every one of these, there's 2, and then I have 2 sets of those, so it's 4 total in our calculations. 2 times 21.2 times 2, so there's the 4. Okay, multiplied by my weight per foot of 3.71. Man, I wrote it wrong again. Pound per foot. Let's clean that up. It looks something kind of like that. And now we have a weight of 315 pounds. So even that's lighter than what we had when we shortened the length into this K or V bracing pattern, okay? So it's the lightest of the piece. Now what's the drawback of this? The drawback that you have is now you have more pieces that you have to work with. They're all lighter, okay? The total assembly of this thing is, 315 pounds. It means each member is only 80 pounds on this. If I just look at one of the members instead of multiplying it, but if we're just comparing costs, it's cheaper in cost, but then the weight of each individual member is significantly less. So 80 pounds a piece. One guy could probably do that. The big burly steel worker, maybe two at most could handle this guy. Okay, so you don't need any extra equipment. I don't need cranes or man lifts to be able to lift this thing or move it around. Two guys can pick this thing up and move it around reasonably well. Okay, I wouldn't want to do 1,000 of them, but a few here or there, as it would be doable if I had to. Okay, the downside is that you clearly have more pieces. Okay, so in theory it would take longer to install it, but it is more efficient cost-wise, and you get big savings in this. So this becomes a very common trick, is to do these double angle bracing patterns, all because of a serviceability requirement of L over R less than 300. Okay, and so that's kind of what we're looking at. So I hope that's made some sense to you in terms of kind of one of the serviceability checks that we do. In our next video, we'll go through and kind of put it all together and show, well, what happens when I know a load, on a member? How do I select the member itself? And we'll show you some approaches to being able to do that. And that's our plan going forward. So anyway, I hope it's made sense to you. If you've got any questions, please be sure to leave them down in the comments below. And as always, if you found it useful, be sure to give us a thumbs up on the video and subscribe to our channel. And we will see you guys in the next video. Happy engineering.